Welcome back. In this lecture, we will discuss some advanced search techniques. So, island-driven search. So the idea is between a start node and a goal node, there are a series of islands that maybe we would have to pass through. So for example, if we think of like a robot that is going through a building and has to go up and down floors, for a robot to go from the bottom floor to the top floor, it has to pass through all the intermediate floors. So we have this additional domain knowledge. So now we could sort of decompose the problem of going to individual floors between the two. And in doing that, we can think of we've decomposed the problem into M islands, or M floors in the case of the robot, and we solve each of these smaller search problems, which ends up having a much smaller depth than when looking at the whole thing. And so this provides a great deal of savings. So the issue is that you have to be able to identify the islands, and it's in doing that you may lose optimality because there might be some path that maybe circumvents an island that gets you a more optimal solution to the goal node. And so you do need a bit more knowledge than just the graph and the heuristic function. But if you do have that knowledge and you can decompose the problem into islands, this is essentially creating a hierarchy of abstractions. And we see this idea come up a lot in various parts of AI on decomposing problems. So in hierarchical constructs, you could think of with a robot, there's kind of an overall plan for the robot to go from the ground floor to the top floor, but maybe there's these intermediate actions that more deal with robotic control of what actions it's going to take to just move a little bit down the hall or avoid an obstacle along the way. So the next advanced search technique we're going to discuss is dynamic programming. So let's assume that we have this function cost to goal n for a given node. And this is the actual cost of the lowest cost path from n to the goal. Now this would be really great information to have because we could think of this as a perfect heuristic function. And we can make all our decisions based on what you see here, where you're just adding the cost to get there plus the cost to get to the goal. So the idea here is perhaps we can use this locally to determine what to do from any given state. And of course this becomes expensive really quick because you got to store the whole graph and you got to compute this cost to goal function for recompute it all the time. So let's just say for now that we can do this. Maybe we can just do it for some of the nodes. So we have this thing, we'll call it expanded. So for a given state, we run expanded and we can get these really exact costs. Now, a great example that you could think of this is going back to our graph. You could say, look at the goal node, and you can go maybe 2 hops back from the goal node, and you have all these nodes that are kind of within 2 arcs from the goal. And for all of those, you can go ahead and brute force compute an exact cost and kind of store it. Once you get to that point, you get to one of those nodes, you can make these really great selections when you get there. And so in that way, we can use this notion of dynamic programming as a source of a heuristic. Because if the graph is very large and the start node is say beyond just a couple hops away from the goal, we can't store everything. And so we're only going to use this expanded function for some of the states. So again, we have our handy admissible and monotone heuristic function h, and we use this to define a new heuristic function h prime, which, if the state is one of these nodes that we allow this expansion of for this more exact computation to the goal, we go ahead and do that. Otherwise, we're going to take the maximum of the cost and the heuristic function, where we're going to say, hey, we're looking for a cost that is less than C. Because here we can, we could say, in the way they've defined the problem on this slide, optimality is defined as looking for any cost less than C. Back in the 90s, when Deep Blue played Garry Kasparov, it actually used a technique like this so that the chess playing algorithm would play perfect chess at the end game. Because when it got to the end game, there were much fewer pieces on the board, so the state space was smaller, and it could do this. It could compute the exact computation. At the beginning of the game, when there's way more states to consider, it's using the heuristic function, and then it kind of arrives at the point that we have here on the slide. So I hope you enjoyed that information about advanced search techniques. Stay tuned for more content.